Get started. So I'm happy to introduce today's one and only speaker, Paul Plucinsky, who has been here at the Smithsonian since 1993. So he predates me, only by a couple of years. And he is the lead scientist for the ACES operations within the Chandra X-ray Center. And I don't think I could do good enough introduction, but he's also my boss. So anyway, Paul's going to tell us about the supernova remnant EO102, which is in the Magellanic Clouds. I can never remember which one's the small one. And he's going to tell us about work that he's been doing with a former pre-doctoral student who has gone back to China, Longji, and Terry Gates. So thanks, Paul.
Great. Thank you. Thanks for that introduction. Okay, so we are going to talk today about, and I will read the source name very carefully, 1E0102.2 minus 72.19. The reason I spelled that all out number by number is that our good friends on the XMM calibration team, who I took this plot from over here, very early in the mission, they started calling it 1ESO102. I keep pointing out to them that that's not the name of the source, but it was entered in their database very early in the mission, and it's just persisted throughout the whole mission. So the science result I'll talk about today is what we're trying to do to measure the expansion of EO102. Since we have a large X-ray crowd today, and since I am the only speaker today, I did add some calibration work for. So those of you that are interested in calibration, this may be interesting. For those of you that aren't, that might be a time to snooze a little bit. Okay, so in case you don't know what EO102 is, and of course we will now call it EO102 because that's much easier to say than the full name. It is the brightest supernova remnant in the small Magellanic Cloud. Here is a beautiful Chandra image from it early in the mission. It's about 45 arc seconds in diameter. So that's about 13 parsecs is the distance of the small Magellanic Cloud. The age has been estimated to be about 2,000 years by Finkelstein et al. In 2006. It's, as I said, it's the most luminous supernova remnant. In fact, it's the second most luminous source in the SMC for X-rays. It's 2.5 times 10 to the 37 ergs per second. Soon after it was discovered, optical spectra were acquired to demonstrate this was one of the oxygen-rich supernova remnants, which at the time it was discovered there were only a handful of these. The abundances of oxygen, neon, magnesium indicate that this probably was the result of the explosion of a massive star, something like 25 solar masses. There's been no compact object detected to date. Of course, Chandra is wonderful to do this. And this central part here is very suggestive. You think maybe that's where the remnant of the explosion would be, but right now there's only an upper limit on it. And the other thing I just want to point out is just how beautiful EO102 looks. Look at this beautiful, smooth outer shock front. It's a little ratty over here. And then there's this very nice ring in here, which is complicated. It has a nice ring-like structure here, but then it has this odd-looking feature here where the curvature doesn't match the rest of the ring. But anyways, this was a Chandra ACES observation from 1999, October, only 19 kiloseconds. And it just shows you what a beautiful image of Chandra. This is one of the most beautiful ones that Chandra's ever acquired. Okay, so now this source has been studied by many, many people. And it's a bit intimidating to come here and give a talk to this audience here because there are people in this audience who have written papers on this source. But what's even more intimidating is that the individual who discovered this source is also in the audience, okay? So for those of you that may not know, Fred wrote this paper in 1981 on the Einstein survey of the small Magellanic Cloud. And in their source list, the second brightest source next to SMCX1 was EO102. And in the discussion section of the paper, Fred said, the second most luminous source is almost certainly a supernova remnant. So congratulations, Fred. You really nailed it there. And I just want to...
I'm glad to see it's getting larger.
Well, I haven't shown you the data yet. Wait to see. But I want to point out another thing that about Fred, which I found really just wonderful. You may have seen there was a paper earlier this year on the New Star team on the absolute flux of the Crab Nebula. And in that paper, the New Star team measured the spectral parameters, the power law index, and the normalization, and then they compared it to the Tour and Seward paper from 1974. And the agreement between the New Star results and Fred's results from 1974 are just spot on, just spectacular, just amazing. So given this, Fred, EO102 and the crab, I just asked if you could save us all a lot of time. Tell us what you're working on today, because that's what we're going to be working on 25 years from now. So anyway, okay, so now what is EO102 as we showed in the X-ray? It looks like this. What does it look like in the optical? Well, it looks very different in the optical. This is from the Finkelstein et al. 2006 paper, which HST data. And now these images are actually on the same scale here. So if you try to look very carefully at where these bright filaments are in the optical, you can see, there is a correlation, for example, with this bright feature in the X-ray. But then there's this bright feature here where there appears to be nothing in the X-ray. And then again, we have a good correlation here. And then if you look at this part up here to the north where the X-rays are very bright, there's almost nothing going on in the optical. Okay, so it really is a more complicated object. The X-rays are perhaps a little bit deceiving. There is quite a bit going on. And then to give you a better idea of the comparison now, here in blue is the X-ray data overlaid on the O3 data from HST again. So that's the same data you showed in the previous image. And now it just makes it a little easier for you to see where there is a good correlation between the X-ray and the optical and where there isn't. And over here is just the contours of the X-ray data overlaid on the optical. So it really is a very complicated object. One of the questions we always ask is, why does EO102 look so simple in the X-ray? Why does Cas-A look like such a mess? And why do these other remnants, G292, look like such a mess? Well, we'll get into that in a bit. I think it's a bit fortuitous that EO102 looks so simple for us. Okay, the other thing we really like about EO102 is it has a remarkable spectrum. It is dominated by strong lines of oxygen, neon, and magnesium. So here is the beautiful RGS spectrum acquired and analyzed by our good friends, the XMM team. Andy Pollack was the one who helped us out a lot this, and Andy Rasmussen wrote the first paper in 2000 on the first RGS spectrum. And you can just see right away how the oxygen 7, oxygen 8, neon 9, neon 10 just dominate the spectrum here. And what makes this so unique is that there's very little or almost no iron in the spectrum. Once you start adding iron emission in here, this region from oxygen 8, around 800 eV, up to 1 keV becomes very complicated, very messy. Now, you'll notice that I've plotted this with a linear y-axis to emphasize how strong the lines are and how the lines dominate. If you look at it on a logarithmic y-axis, then of course you start to see all the interesting weaker lines that are here in the spectrum, okay? But when we saw, we knew how simple this spectrum was, how beautiful it was, we came up with the idea that the gratings on XMM and the gratings on Chandra could characterize the spectrum very well, and then we could use that to calibrate our CCD instruments, which we were struggling to calibrate with in this low energy bandpass because our onboard calibration source is the lowest energy line we have at 1.5 kV. We had a weaker line at manganese L at 670 eV, but that's now faded as the mission's gone on. So we started using EO102 for calibration. So now I'm going to jump into, now that we've shown the image and the spectrum of EO102, so you have a basic idea what it is, I'm going to jump into the calibration. And this is where I want to mention this group that we've been working on, the IACHEC, which is one of the most tortured acronyms in all of astronomy. It's the International Astronomical Consortium for High Energy Calibration. One of the things we wanted to do is we wanted to identify objects that we could potentially use as standard candles in X-ray, develop a standard spectral model, and then apply it to all the different instruments. So this is a project that we've been working on for a long time now. We wrote 2 SBIE papers, one in 2008, one in 2012, and now our last paper was an ANA just earlier this year, 2017, taking this standard model and applying it to all the instruments on the active X-ray missions that are flying right now. And the basic idea is you go back to that beautiful RGS spectrum in HETG where you can just see the lines and identify all the lines. You know the energies of the lines, you know the relative strengths of them, and we built an empirical model which is based on 52 Gaussians for all the lines. And then we use an APEC no-line continuum, and you can talk to Adam and Randall about the APEC no-line. This is a version of APEC that removes all the line emission, just keeps the continuum components. And of course, we have absorption within the SMC and within the galaxy. And then we fit it to the CCD data. Now, when you take that beautiful RGS spectrum and you fold it through the CCD response and you blur it out, this is now an XIS spectrum from Eric Miller at MIT. You can still see you cleanly resolve the oxygen 7 triplet from the oxygen 8 Lyman alpha line, the neon 9 triplet from the neon 10 Lyman alpha line. So this is why it was so useful for us to have this as a calibration source. And underneath you can see where Eric has plotted the contributions from the models in the line. So this is the oxygen 8 Lyman alpha line that's contributing here. There are 3 lines here for the oxygen 7 triplet, the forbidden line, the resonance line, the forbidden intercombination, the resonance line, which then sum up to produce the oxygen 7 peak. And same thing for the neon 9 triplet, neon 10. And so when we use this model for calibration, the energies of the lines are frozen, the widths are frozen. The only thing that we allow to vary is the normalization of the line. And we use this to try and compare the effective area of the various instruments. And let me just point out that, this, as I said, this is many years worth of work. Some of these people have since retired or are semi-retired now, and we've been working on this for so long. And I just want to point out Dan Dewey at MIT and Andy Pollack, who are both so instrumental in doing the hard work in characterizing grading spectrum. And then we have the rest of the members from the XMM team and Suzaku and so forth. And I just want to make sure that this community is aware of this paper. If you need a reference for how the effective area of Chandra or XMM varies over the course of the mission, or if you've got results early in the mission to later in the mission and you want to know if I see some change or variability, is it significant, and it's in this low energy bandpass, this is the reference that it could be very useful for you. So please make use of this reference. This is in our last paper here in 2017. Okay, so now this is the summary plot comparing all the instruments. So this is where we selected what we thought were the best observations of EO102 and the best calibrated modes, and then we compared the normalizations that we got for each of the instruments. So for each instrument, there's 4 data points here. The black is the oxygen 7, red is the oxygen 8, green is neon 9, and blue is neon 10. So for example, here there are 4 data points for the RGS. And since this model was really heavily built on the RGS data, I've plotted everything relative to what we have in the model here. And the RGS, of course, agrees quite well because the model was heavily derived from that. Now, you should not assume that what's in the IACHEC model is the true value. It's just a reference, okay? So please don't think because somebody agrees with this value that means they're correct. We're using this to provide a comparison between the various instruments. So here we have the results for the MOS1 and the MOS2. Here we have the results for the PN. And you can see, this is something we've been talking with the XMM team about an awful lot. For whatever reason, we still have MOS fluxes that are coming out 5 to 15% higher compared to PN when we look at EO102. That's not what they see when they look at point sources on axis. They see the MOS more like 5% higher. So we're really not sure why this is happening. They're still investigating that. Here are the points for our favorite detector, ACES S3. You can see we have this very interesting energy dependence where the oxygen 7 is the lowest, then the oxygen 8, and then by neon 9, neon 10, we seem to be agreeing better with everybody. So this makes you wonder, do we really have the contamination model right for ACES? Then we have the 4 XISs from Suzaku and the XRT from Swift. So just to remind everybody, in case you haven't looked at this is what we're up against with the calibration of Chandra ACES. Here are 3 observations of EO102 taken in this almost exactly the same position, the same mode, from 2003, 2012, and 2016. These are the observed spectra of EO102, and it's obvious to everybody the count rate is going down with time. The contamination layer on ACES is getting thicker and thicker. These are now all fit, again, with the standard IACHEC model, and they're all fit with the same line normalizations here. So you can see that the same model fits all 3 of these data extremely well. And that gives you an idea of how well we're doing with our contamination correction. So many thanks to Akos and Herman and Alexei for working so hard on this. But the thing that's really shocking is just, if you just look at that oxygen 8 Lyman alpha line, we can see, we've lost, just 2/3 of our collecting area just in this time frame. Okay, so for those of you that are analyzing ACES data, how well does ACES agree over time? So what I've done here now is I've taken the normalizations for oxygen 7, oxygen 8, neon 9, neon 10. I've just plotted them as a function of time. The black solid line is the average of the on-axis values. Now here in this plot, I've included some of the data where we take EO102 and we push it off toward the top or the bottom of the S3 CCD, because of course we have to get the spatial model of the contaminant right. So those are the blue squares and the green squares, the ones that are at high chip Y or low chip Y, far away from the aim point. The red data points are the ones that are on the aim point. So that black line is the average of what we get at the aim point. And then the red line is what the IACHEC value is. And then the dashed black lines are just plus or minus 10% to help you see when things are changing by more than 10%. So if you're really doing some science early in the mission, later in the mission, you need to know how good the ACES calibration is in this energy range. We hope that this plot is useful for you. So you can see at oxygenate, on axis, we're within plus or minus 10% at any point in time throughout the mission. When we get a little bit off axis, there are some interesting things going on here that maybe our spatial model isn't quite right at that point in time. And then when we get to the neon 9, neon 10, where the contaminant is less important, we're also doing fairly well there. And where we have the most difficulty is at the lowest energy with the oxygen 7 line. Okay, so this is what it looks like for S3. Now, I've plotted it this way so that we can have a simple comparison with the I3 plot. This is now the I3 plot. And again, it's the same format. The black line is the average of the points that are close to the aim point on I3, which we all know is now at high chip Y and I3. And you can see, for the most part, we're doing pretty well, plus or minus 10%. But, there are some interesting differences between S3 and I3. And if I just flip between these two, you can kind of see. So if you look at, for example, where that black line is for S3 for oxygen 7, you can see it's a significantly different place. We're about 10% lower on average on the I array than we are on S3. Oxygen 8, we have better agreement between the two. I mean, the black lines are almost right on top of each other. And then neon 9 is something that we really don't understand why we're seeing this type of behavior here, but neon 9 is significantly different between I3 and S3, but then by the time we get to neon 10, they agree very well again. So, okay, so that's the status of what the calibration and function time looks like on I3 and S3. And I emphasize this because we're a big Chandra audience, but in the paper we also have the time dependencies of all the other instruments. So if you want to know MOS, this is Steve Sembe's plot showing the MOS time dependence. This is Frank Hobel showing the PN. Eric Miller doing it for all the XIS instruments, and Andy Beardmore doing it for the XRT. And I just want to point out that the PN is the most stable instrument of all of them. The PN gives remarkably consistent fluxes over the course of the mission. But that doesn't mean the PN is right in terms of absolute effective area, okay? The PN is very stable, it's very consistent, but we think the PN isn't the best measure of the absolute flux for other reasons. But okay, all right. So that's the end of the calibration part. We're going to go on to science. Does anyone want to ask questions about calibration before I move on, or good? If you have any complaints, complain to Akos because he's responsible now. So okay, all right. Let's go to the expansion of EO102. Okay, so early in the mission, there was this very interesting paper by Hughes et al. That took one of the very first data sets of Chandra, of EO102, and then compared it to the Rosat HRI image, and then compared it to the Einstein HRI image to determine the expansion of EO102. And they got a result that EO102 was expanding at 0.1% per year, which is about 0.022 arc seconds per year. And this implied a shock velocity of 6,000 kilometers a second. But the X-ray spectral fits gave temperatures somewhere between 0.4 and 1 keV for the shock. And if the shock is really going at 6,000 kilometers a second, you would expect a much, much higher temperature, something more like 45 keV. Okay, so there was this apparent discrepancy here between what you were implying for the temperature from the X-ray spectral fits and what you thought the temperature should be from your expansion measurement in the shock velocity. So they explored various explanations for this. One is non-equipartition between electrons and ions, and that can explain part of this discrepancy, but even with the most extreme assumptions, there's just no way they can get it that temperature down below 2.5 keV. So they thought there was still a discrepancy between the X-ray temperature and what you get from the shock velocity. And they concluded that a significant fraction of the shock's energy was going into the acceleration of cosmic rays. And that's why there was a discrepancy between these measurements. So in the paper, they talked about their fitting method that does a global mean expansion, and that it assumes the expansion rate is uniform over the entire remnant, both radially and azimuthally. And they estimated an age about 1,000 years, which, as I'd mentioned earlier, from Finkelstein et al. From the optical day, got something more like 2,000 years. So, and then here's their plot of their two data points. Again, the one with the shortest time span is comparing Chandra to Rosat, and the longer time span is comparing to Einstein. That's a baseline of about 19 years. Okay, so there are some complications with this global expansion measurement, and they're comparing data from 3 different instruments, 3 different telescopes, 3 different detectors. And of course, as we all know, Chandra is the one that has absolutely the best angular resolution, the 50% encircled energy, about 0.4 arc seconds. And Einstein and Rosat, have resolutions more like 4 arc seconds or 5 arc seconds. And if the blast wave was expanding at this 0.1% per year, and the radius is 22 arc seconds, in 19 years, the outer blast wave has moved about 0.43 arc seconds. So you're trying to measure something moving 0.43 arc seconds, but you've got Einstein and Rosat where the resolution is 4 or 5 arc seconds. So it's a very difficult thing to do. The other point is EO102 is a very complex three-dimensional structure, and we're going to talk a little bit more about this. In their analysis, they're using all the data, and that inner ring where the ejecta are, we'll talk a bit more. It's very complicated. So there's data both from the optical and the X-ray just indicating how messy that is, and we'll talk about that in a few slides here. And then the ACES data in full frame mode also have the problem that they suffer from pileup. And that bright ring in EO102 is bright enough that there's significant pileup there, so the count rate is being depressed in the bright ring. And so one has to wonder if the Chandra data have the bright ring being artificially depressed by pileup, and you're comparing to Rosat and Einstein that don't have the effects of pileup, how does that affect this measurement? Okay, so quickly, just here again, here's this beautiful Chandra image, and I'll just point out these 2 features here we're going to call the southeastern arc for the rest of the talk. That's that very bright region here, the ejecta, and this is known as the northern shelf up here. And here is an estimate of the pileup fraction from the observation that was used to do this analysis. And in this image over here, orange means about 5% for the pileup fraction, and white is 10% or higher. And you can see the brightest parts of the remnants are the ones, of course, that have the highest pileup fraction. Okay, now is Kathy Flanagan here? Because I've talking about all these people who have written these beautiful papers. Well, Kathy has a beautiful paper in 2004 looking at the HETG data in EO102, and there are just many great results in that paper, and I just want to highlight 1 or 2 of them. And this is the evidence that we have from the X-ray data that there's a complex 3-dimensional structure in the ejecta ring in the EO102, that there's red-shifted and blue-shifted material. And so Kathy has this very nice figure in her paper trying to help you understand what the effect is and how they were able to measure this with the grating. It's one of the neatest measurements that Chandra's done. So if you look at this white image here in the center, there are these 6 different figures here. So just pay attention to the top row here. This is an example to explain what the effect is and how the gratings can actually measure it. The bottom is their idea for EO102. So just focus on the top row now and focus on that image here in the center, which is m equals 0, which would be the 0th order image from the gratings. And imagine that you could magically construct an object which was a ring, and half the ring was red shifted and half the ring was blue shifted. Okay? So this orange thing is the part that's red shifted, the blue is the part that's blue shifted. And then ask your question, if you had an object that had that type of spatial structure, and then what would the dispersed image look like with the grating? Well, the red shifted part is going to get shifted to higher wavelengths by the grating, of course, and the blue shifted part is going to get shifted to slower wavelengths. So when you take a circular structure like this, if it really was half red shifted and half blue shifted, on the minus first order, it would kind of expand the ring along the direction of the dispersion. So on the plus first order, you would actually collapse it, okay? So this is a really interesting feature that they were very clever and they figured out about the grading. And they could use the comparing the minus first order to the plus first order to learn something about the blue and the red shifted material in the object they were looking at. Okay, now this top row, this is not what they think is happening in E102. Their model is what's here below, is that there are two rings, or most of the ejecta is in two ring-like structures, and these two rings happen to overlap along the line of sight. One is blue shifted, one is red shifted. And so when you disperse that into the minus first order, if they were displaced in this way on the sky, then they start to come together in the minus first order, but on the plus first order, they get separated. And this is showing you down below, this is what the minus first order, the zeroth order, and the plus first order look like with the MEG for the neon 10 Lima alpha line. And sure enough, that this is the structure that they're starting to see. And so they believe that there really is a ring of blue shifted material and a ring of red shifted material. Now, of course, you can tell, we're dying for statistics here. It's a hard measurement to do. Okay. Yeah, and then I would point out that there's also been beautiful work done in the optical by Voigt and Dopita, and they conclude that E102 has this asymmetric bipolar structure. They don't have maybe exactly the same model as most of the structure, the ejecta being in these two ring-like structures, but it's a pretty similar idea that there definitely is blue shifted and red shifted material in that ejecta ring. Oops, shit. Oh, sorry. There we go. Thank you. Okay. All right. So years ago, Dan Dewey had presented this idea. So what he was thinking was happening with E102, again, this is building on the same thing. In our projection in 2D that we're observing, we see these two rings that are overlapping each other. And what he thinks is that we're looking down the barrel of maybe a cylinder, and we're seeing maybe one edge of it is blue shifted, and the other edge is red shifted. And then we're somewhat tilted, our line of sight is somewhat tilted to the major axis of the cylinder. And so he came up with this nice little cartoon diagram, and Dan was playing with lots of different models. So you can put lots of different structures in here for the cylinder. But what I want you to think about now is what we really want is this outer blast wave. If we want to try to measure expansion of E102, we should use Chandra's resolution to look at the outer blast wave. The ejector ring is fascinating. There's lots of great physics going on there, but it's very complicated. What we want to do is look at the outer blast wave. And if we can do that, then we don't have to worry about all the complexities of what's happening with the inner ejector ring. Okay, and then here's some other more papers showing that one idea what we think was happening, this is from Terry's paper very on, 2000, showing that the oxygen 8 emission peaks at a higher radius outside the oxygen 7 emission, which is further in. So the idea is that bright ejector ring is the reverse shock making its way through, and as you go closer and closer to the remnant, you're seeing material that was more recently shocked. So the stuff that's further out was shocked for a longer period of time, and that's why you see it at the higher ionization state. And then Kathy had a figure in her paper showing how in the northern shelf and the southeastern arc, how you show that what the ionization timescale is increasing as you go through this material. Okay, so now, as I said, our approach, we hope, is simpler and different. We're going to use only Chandra data and compare only to Chandra data. I don't want to know anything about systematic uncertainties, Einstein and Rosette. I'm too old for that. I only going to look at Chandra data. We're going to look only at the outer blast wave. We're not going to look at the ejector ring. The Hughes et al. Analysis used all the data. And as we said, that inner ejector ring is very complicated. We just want to look at that smooth outer blast wave. And then we're going to minimize or eliminate pileup by looking at the outer blast wave, which is fainter, but also we're only going to be using the subarray. So now, that all sounds great, but of course there's complications with our approach too. We have problems here. I say I only want to use Chandra data to remove those systematic uncertainties, but of course the mirror is the same for all these measurements. We have no evidence the mirror has changed with time, but we have lots of evidence that ACES has changed with time. So every time we do a measurement with ACES, if there's a time difference of a year or more, it really is a different detector every time. So we have to take that into account in our analysis. The outer blast wave is faint, so that's good that it reduces pileup, but it's bad in that your statistics are worse. Some of these observations we're going to be using are only 8 kiloseconds long, so we're going to be severely limited by the statistics in those. And ideally what you'd like to do is you'd like to register all these images together using bright point sources in the field of view. But if you've only got an 8 kilosecond observation and you're in a subarray looking at a very small piece of the sky, many of these observations don't have any bright sources that you can register on. So we have to find another way to register these images. And this all sounds like a lot of hard work, so that's why Terry and I weren't going to do any of the hard work. So we had to get Longji to come help us out here and do lots of the hard work here. So Longji was here for about a year, and now he's back in China now, and we're finishing up this analysis, and hopefully it'll be part of his thesis. Okay, so here's a beautiful image that Danny Milosavljevic provided me with, giving you a little bit more detail on the red shifted, blue shifted structure in the optical mission. So these are data that Danny has from Hubble. And the material that's color-coded blue here is blue shifted material. The stuff that is this reddish, yellowish color is red shifted. And the green is the stuff that is closer to having zero velocity. So you can see how complicated the structure is. So yes, you have this green structure that's out here that's close to zero velocity. And then you have this stuff which here looks mostly red shifted, and you have this big glob of stuff which is blue shifted here, but not very far away from it. You've got red shifted stuff, and you've got stuff at zero velocity. So in the optical, this is very, very complicated. But what I want you to focus on is I want you to focus on this bright central region here, which is blue shifted, okay? Okay, so presumably that is coming at us. It has very little velocity in the plane of the sky. And if you compare that to the X-ray data, that is this central knot right here, okay? So we decided that we were going to use this central knot, and we were going to register the X-ray images to each other using this region here, okay? And we're confident that there's very little motion of this region in the plane of the sky, that if it's any motion, it's mostly coming at us. Okay, the other thing that you want to do is you want to make sure when you're talking about the blast wave, you really are looking at the blast wave. You aren't looking at the ejecta. And again, the spatial structure is very interesting in EO102. The region we want here is this very smooth outer shock here, and we want to convince ourselves this really is the blast wave, and it's not any ejecta emission here. And of course, with Chandra, we can go and we can extract spectra in these very small spatial regions and look for differences here. And so just to convince ourselves, we extracted spectrum from here, and we compared it to this region here, which isn't the brightest part of the ring, but you can see it looks like it kind of has these fingers sticking out from this ring of ejecta emission, and then our bright central knot. And when you look at the abundances that you get there, for this region we call the blast wave, we're getting a temperature about 3/4 of keV. The oxygen, the neon, the magnesium about 1/4 to 1/3 solar, which is typical of what you would get for abundances in the small Magellanic Cloud. The ejecta emission, this region here, which again is not the brightest part of the ring, we're getting oxygen abundances and neon that are 2 or 3 times solar, and the bright central feature, we're getting something 2 or 4 times solar. So all this region here has a lot of ejecta emission in it here, but this region out here really is consistent with just swept up blast wave and the small Magellanic Cloud. Okay, so we're going to go and we're going to extract radio profiles on these different directions. This is just giving you an idea of where we are going to fit, and we're going to try to look for expansion for. And again, the part that we're really, really hopeful to get a result from is this very smooth outer shock here. You can say if we have any hope of measuring expansion of EO102, this is the place where we're going to measure it. And of course, we need to have a model that we're going to compare to the data. So this is Longji taking the model, folding it through the point spread function, giving an idea. This is the model that we're going to fit to the data. And now here are 2 radio profiles I've picked from an observation in 2008. And so the way we did this is we go back to the earliest observations. We construct a model of what we think EO102 is. We register all the later observations to that model. And then we extract these radio profiles and we fit this model to it and see if we can see any difference that can be interpreted as an expansion. So this gives you an idea how difficult this measurement is going to be. You can see those are the data points and those are the uncertainties on the data points. So this is where the short 8-10 kilosecond observations are making it very difficult for us. In these 2 particular directions, so the red line is the later observation, the blue one is the earlier one. You can see there's an evidence of some small expansion there. And then if I show you some data from 2015, this is now a different angle where the structure is a little bit different, so it peaks here. You can see we hope that we're measuring a little bit of an expansion here, but as you can tell, it looks pretty small. And if we try and compare that to the Hughes et al. Result, this is what we get, okay? So now this is the expansion rate, so percentage per year. The purple line here is the Hughes et al. Result with the two data points coming from the Einstein and the Rosat comparisons. The green data points down here are our data points, okay? And you can see we have many more observations over the course of time. And then the blue line is the expansion rate that's coming from the Finkelstein paper and the optical. And you can see none of our data points are really getting close to what we have the Hughes et al. Result. They all seem to be fairly consistent with each other. There is significant scatter here, and there is a little bit of a downward trend here, which is a bit concerning. But when you look at this, this really does look rather different than what the Hughes et al. Result was. If we, instead of measuring expansion rate, we just compare velocities, this is now the velocity from Hughes et al., the velocity from the optical, and our measurements. So we're getting a velocity something just a little less than 2,000 kilometers a second. The optical expansion is that, and the Hughes result was 6,200. Now, the optical filaments are different material, and they're at a different location, the remnant. There's no reason that they should be moving at the same speed as the outer X-ray shock. So it's a coincidence that the X-ray shock and the optical filaments are coming up with similar velocities. And what we think is that there's been significant deceleration of the outer blast wave. The X-ray emitting material, the outer blast wave must have been moving faster than that to get further out where it is in the remnant now. But now it just happens to slow down that it's going similar to what the optical is. So if we assume there's been no deceleration of the optical, but there has been deceleration X-ray, this gives us a deceleration parameter of something like 0.6. So this indicates that EO102 is somewhere intermediate between the free expansion phase and the set-off phase. Because for a set-off phase, you expect something like t to the 2/5. Okay, so the bottom line here is, looking at all these data sets we've done here, it looks like we're going to get a significantly different expansion result. In fact, even with Chandra, we're really struggling to try and measurement. You saw those radio profiles. I mean, this is not an easy measurement to do. Okay, and then I just want to go back quickly and revisit this issue of the electron-ion temperature ratio, because this is another issue that the Hughes et al. Discussed. So this is a paper from Van Adelsberg et al. 2008, where this ratio has been measured for several remnants here. Some of the remnants I'm sure you're familiar with. And then now we've just plotted on the value here that we get for EO102. So again, our shock velocity is just a little bit shy of 2,000 kilometers per second. And this is the ratio of the electron temperature, the proton temperature that we're getting. And you can see, it's fairly consistent with what people are getting for other. There's really no great discrepancy here. And again, the Hughes et al. Result had an expansion velocity out here at 6,200. So a very different result. Once we get something more like this, then we seem to be more consistent with these other remnants. Okay, so just wrapping up, expansion measurement with Chandra data alone is significantly less than the Hughes et al. Result. Again, we're getting something a little bit less than 2,000, which happens to agree quite well with the Finkelstein results, but again, that's just a coincidence, we think. And because of this, we think there's been significant deceleration of that outer blast wave in EO102, which 2,000-year-old remnant running into ISM, you'd expect there would be some deceleration. The electron temperature we get from the X-ray spectral fits and the shock velocity can be explained with only modest non-equipartition between electrons and protons, so we don't think we have to appeal to any extreme cases here. And we think it's the electron-ion equilibration rate seems very comparable to what we're seeing in other remnants. Okay? All right, so that's all I have.
Okay, so thank you, Paul, for that very interesting enlightening talk. And I just want to say that before we go to questions, don't leave at the end of questions because ACOS has to make an announcement.
Ooh.
Are there any questions?
John.
I was wondering if you had any inclination to try to measure the reverse shock velocity.
Yeah, I mean, there's beautiful data there. There's more counts. It's going to be complicated. we have to worry, 2,000-year-old remnant, and we got a 15-year baseline with Chandra, so I think it'd be very interesting to do.
In the southeast, there's like a nice sharp edge.
Yep. I think that's definitely on our list of things to do, and hopefully this methodology that Lung is working on, we can hopefully easily apply to doing that for the reverse shock too. So.
For the electron ion, all those other ones you showed are done with H alpha, and so they, first of all, are shock waves that have some neutral fraction, but also you're measuring the electron temperature very close to the shock front. Here, because this is at the SMC, you're actually integrating over quite a bit of stuff, so there's some Coulomb equilibration, and in principle, the electron ion equilibration at the shock could be noticeably lower than what you're measuring.
That's true, yeah. I mean, we're trying to use Chandra's resolution, but you're right. I mean, this is 60 kiloparsecs away. We don't have the resolution that they have for the galactic remnants, Yeah.
Is it worthwhile looking at XMM data on this object?
We do all the time. we do it for calibration purposes. It's just XMM, because their point spread function is so different. I mean, you any type of spatial structure you just can't do with XMM. I mean, EO102 looks like a fuzzy donut for XMM. So, but the spectra are beautiful. Yeah, I mean, the MOS spectra are absolutely gorgeous, and the PN spectra we have our issues with, but the MOS spectra are very good. So. Yeah.
Dan, remind me, Cas A forward shocks around 5,000 kilometers per second?
Yeah.
Is that right? The optical material is moving about 5,000 kilometers per second.
Yep.
So the relationship's not so unusual.
But Cas A is 350 years old. This guy is 2,000. So this guy is older than Cas A, but had 6,200 kilometer per second shock velocity.
So is ours J1713. Has a fast shock.
What's the shock for that?
Years old. It's probably 4,000 kilometers per second. A couple thousand.
Yeah, interesting. Yeah, see, I would have taken what you said and used an argument for a lower shock velocity. So yeah, so Cas A is 5,000. Yeah.
But it's speaking, Dan just said, about the environment so much as the explosion itself.
Yeah, EO102, that's why I was surprised that latest Voigt paper where they're getting this 7.5 per cubic centimeter for the pre-shock density. It seems a little high because it looks like it's in a fairly low density part of the SMC, so.
If there are no other questions?
Nope.
Yeah, another question from Dan.
I missed it, but there's no hint of a non-thermal component.
In the X-ray, yeah. We fit the spectrum with two continuum components. One has a temperature like 0.2 keV, the other one has a temperature like 1.2 keV. The constraint on the 1.2 keV Bremsstrahlung is, not particularly good. It's weak, but of course, could there be some non-thermal in there? Perhaps, but if there was, it's very weak. I don't know if New Star's looked at EO102. I know they've looked at N132D, but I don't know about EO102, yeah.
How do the results compare to G292? Because the age is probably not that much different. It's also oxygen rich.
Yep, G292 is oxygen rich, and G292, you look at it in the X-ray, it's so much more complicated than EO102, so you have to think we don't have this fortuitous viewing angle that we have at EO102, where we're looking down this barrel of the cylinder or whatever it is. It's much more complicated. Yeah, I haven't tried to compare EO102 to G292 that much, but it's obviously a lot more complicated than.
There's no, presumably there's no historical observations of this event, right? I mean, 2,000 years old, you sort of may expect that, whereas you must be getting something more like 6,000 at this point, is that right?
No, 2,000 we think is consistent with or it's, Hughes et al. Was arguing for 1,000, and 2,000 is probably, yeah.
I mean, 1,000 you would
Right, so they're right. There is no historical record, and I don't know if has Armin Rest done the light echo for EO 102? I don't think he's done the light echo to try and figure out what type of supernovae it was and how bright it might have been. Yeah, I can't.
Doesn't.
Yeah,
And I don't think he's done anything over 700 years.
I see. Right. Yeah. Yeah. No historical record. Yep.
If there are no other questions, let's thank Paul.
Yeah.